The first ionization energy for various elements is shown below. As you can see, there's a periodic trend to it. Atoms which are on the left side of the periodic table have the lowest ionization energies, and atoms which are on the right side of the periodic table have the highest ionization energies. So what that shows is it doesn't take as much energy to liberate lithium's valence electron as it does to liberate, say, a helium electron. So even though helium and lithium have similar numbers of protons and electrons, there's a big difference in the energy required to pull an electron away from a helium versus pulling it away from a lithium. The trend that we see is the first ionization energy increases as we go to the right on the periodic table, and we also see that that ionization energy increases as we go up on the periodic table as well. So that means that this helium is going to have the highest ionization energy, it's called. And atoms here in the lower left would have the lowest. Let's fill in the blanks to these statements. According to the table, the first ionization energy for beryllium is greater or less than the first ionization energy for boron. So beryllium is here, and boron is here. Is the energy required to liberate a beryllium electron greater or less than the energy required to liberate a boron electron? And so even though we do see this trend that the ionization energy tends to increase as you go to the right, it doesn't always hold. And we can see that in the diagram above. So boron is here having a first ionization energy of around 800 kilojoules per mole. But between lithium and boron is beryllium. And that is actually this point on the diagram. So beryllium has a higher first ionization energy than boron. Beryllium could be 900 something. All right, so this one has the higher ionization energy. And boron has a lower ionization energy than beryllium. That shows that this trend does not always hold. We can see that in the scatter plot above. So what factors could lead to beryllium having a higher ionization energy than boron? Well, one factor is it has a nice complete 2s shell. See, beryllium would have 2 electrons in that 2s shell, and that's all that the shell can hold. And so that tends to be a stable configuration, and it's tougher to pull an electron away from that stable configuration than it is in the case of boron. See, boron would have the 2s filled, but it would have 1 in the 2p. So if we look at their configurations, beryllium's configuration is 1s2, 2s2. But boron is going to be 1s2, 2s2, 2p1. It turns out that that 2p1 electron is fairly easy to pull off. And that's why it has the lower ionization energy of the two. All right, so we'll put that beryllium has a greater first ionization energy. So now they're asking us about the reason why, and they're comparing the energy of the 2s subshell to the 2p subshell. So if we go back into our past of looking at the energy level shells, we see that the 2p is at a higher energy level than the 2s. which means that the 2p, it's going to be easier for electrons to be pulled away. So the 2p shell is at a higher energy than the 2s shell. So the 2s then is at a lower energy level than the 2p. That'll make it actually harder to remove an electron from the 2s. The more energy they have, the farther on average they are from the nucleus, the easier they are to pull off. And this is a trend that we generally see. Each time a new subshell begins, the ionization energy of that element will be less than the previous, making that element actually easier to ionize. If we look at the table, we can see this. So beryllium represents a completed 2s shell. Boron would be a start of a new 2p shell. So there's going to be a drop in ionization energy. Same thing happens here. We've got sodium and then magnesium. Mg, magnesium is here. So when we jump across the gap to aluminum, we do see a drop in ionization energy. So another exception to the general trend in ionization energy involves paired electrons and orbitals. Turns out it's more difficult to pull an electron away if it's alone versus if it's in a pair. And the reason is that the electrons repel each other. So if you have a shell, like let's say you have a 2p orbital here, if you've got two negative charges inside that orbital, they will repel each other, making them want to get away more. And so it's going to be easier to steal one than it would be if we just had a 2p orbital with just one electron in it. So this is more difficult to steal. This one's actually going to be easier to steal because of the repulsion. So to answer the question, we want to see how does the ionization energy for nitrogen compare to that of oxygen. So the order of the elements is boron, carbon, nitrogen, oxygen, and fluorine. We see oxygen is here, and there's nitrogen next to it. Nitrogen has a higher ionization energy than oxygen, according to the table. So why is this? Well, we could complete an energy level diagram for both of them to explain why it's easier to take an electron from oxygen than nitrogen. So to make the energy level diagram, we'll just do a blank for the 1s shell. We can do a blank for the 2s shell. And then we're going to have 3 blanks in a row for the 2p. All right, so let's do the same down below. And one of these diagrams can be for nitrogen, and the other one's for oxygen. So both of these elements are going to have electrons in the 1s shell, no question about that. Both of them are going to have a full 2s as well. Now when it comes to the 2p, we see that nitrogen has 3 electrons in the 2p, and oxygen has 4 electrons in the 2p. According to Hund's rule, the 3 electrons that nitrogen has will go into their own orbitals, like this. So for oxygen, we're going to fill those orbitals separately first with 3 electrons, and then there's one more. It's going to be forced to form a pair here. So whereas in oxygen's diagram we have a pair, In nitrogen's diagram, we don't have any pairs. They're all lone electrons, and those are more difficult to remove. So it's actually going to be easier to steal an electron from oxygen because this pair is repellent itself. The electrons in it don't want to be near each other, so they're happier to be stolen. All right, so for that reason, the first ionization energy for nitrogen is actually going to be greater than the first ionization energy for oxygen. The second ionization energy is when we're taking an atom that's already been made into a positive ion and taking one more electron from it, causing it to form a 2+ ion. Some atoms will do this very easily, whereas with others, it's very difficult to make them into 2+ ions. Sodium is an example. Sodium easily forms a 1+ ion because it'll lose that one electron that it has in the outer shell. But it is very difficult to make sodium into a 2+ ion by removing a second electron. It would rather keep its complete shell of 8 that it has rather than go to an outer shell of 7. And what I mean by that is sodium has 11 protons in the nucleus. So what I've drawn here is a sodium +1 ion. So let's assume that sodium here has lost one of its electrons, and it's now forming a sodium 1+ ion. It likes having that complete shell of 8 in energy level 2. It doesn't want to lose that 8 that it has and go to 7. And so we're going to find that pulling a second electron off of sodium is fairly difficult, and it takes a lot of energy to do so. That can be seen right here in the first and second ionization energies for sodium. So we see here that the first ionization energy for sodium is quite low, the lowest on this particular chart. But we see that that second ionization energy is huge, 10 times as much almost. So that just shows that it's easy to pull off the first electron for sodium, but it's very difficult to pull that second electron off. So in general, that's always the case. The second ionization energy is greater than the first ionization energy. That's true of all the values. So we find that it takes more energy to pull an electron off a positive ion than it does to pull an electron off a neutral atom. So why would this be? That's because the positive ion attracts the electron more strongly. So imagine you're an electron. You're near a sodium plus ion, and then compare what that would be like if you were near just a neutral sodium. Well, we know that the sodium ion's charge would be +11 -10, because it has 10 electrons, which leaves it positively charged with a +1 charge. But sodium itself would actually be neutral. And so if you're neutral, then you're not going to be as attractive to an electron as if you're positive, is the idea. Next question says, how much energy would it take to ionize 1 mole of magnesium atoms by removing 2 valence electrons per atom to form 1 mole of magnesium 2+ ions? So the values given in this table are kilojoules per mole. So if we just go to magnesium, we'll see how much energy it takes to remove the first electron. So for the first electron, it's going to be 738 kilojoules per mole. And then when we go to remove the second electron, that is 1451 right here, kilojoules per mole. So let's add them together. I get 2189 kilojoules per mole. So when they ask how much energy does it take, the answer should be written as 2189 kilojoules. Next question says, how much energy would it take to ionize 4 moles of aluminum by removing 3 valence electrons per atom to form 4 moles of aluminum 3 plus ions? Alright, so we're going to have to add the 578 plus the 1817 plus the 2745. We're going to pull 3 electrons off of aluminum. So I get a total of 5,140 kilojoules per mole. But keep in mind, it asked about ionizing 4 moles, not just 1 mole. So I'm actually going to multiply that result then by 4 moles. We'll see that the moles will cancel here, and we'll be left with kilojoules. So I get 20,560 kilojoules then. Next question says, disrupting a stable configuration requires significant energy. We see that here with sodium. It only requires 495 kilojoules per mole to get rid of the first electron, but it takes 4,562 kilojoules per mole to get rid of the second one. We want to know what noble gas has the same electron configuration as Na+. If we go back to the periodic table, we can see that when sodium loses an electron, it will have the same configuration as the noble gas neon. So that'll be the answer to this question. Enthalpy is the energy required for a chemical process or reaction to take place. And enthalpy has the symbols delta H. A positive enthalpy indicates that energy is required to be put into the system in order for the reaction or process to take place. It's called an endothermic reaction when energy has to be sucked in from the surroundings, and often this is observed as a cooling down of those surroundings. So if an endothermic reaction is taking place, when you touch it, you may feel cold because it's actually pulling energy out of you. A negative enthalpy, on the other hand, shows that energy was released by the system, and it's a loss of energy of the system to the surroundings. It's called exothermic, and that's when energy is given off, and often we observe an increase in temperature for the surroundings when an exothermic reaction takes place. So if we were to touch an exothermic reaction, we would feel hot because energy is flowing out of the reaction to us. Here's a couple simple examples. A cold pack combines a chemical such as ammonium chloride with water. Now, normally the two are kept separate when the cold pack's not being used. So you can break the barrier and let the two mix. And when they do, it can be used to cool things down. So what type of reaction is taking place when you break a cold pack and combine ammonium chloride with water? Is it exothermic or endothermic? So this is a classic example of an endothermic reaction. When you touch the cold pack, it feels cold to your touch. And if we just draw a heat flow diagram for this, we could show what it's doing. It's pulling energy out of you and putting it into itself. That is an example of endothermic. And this will feel cold for that reason. Now let's look at this. When hydrogen gas is burned, which means it's reacting with oxygen, would that be an exothermic or endothermic reaction? Well, if you have a balloon that's filled with hydrogen and you light it with a flame, the balloon will explode and it will give off heat when it does. So this is a classic example of an exothermic reaction. Heat will be flowing from the balloon to the environment, and we give that heat flow the letter Q often. All right, so the electron affinity of an element is the energy change that takes place when an electron is added to an atom in the gas state to form a negative ion in the gas state. There's an example below for chlorine gas being ionized by the addition of an electron. So neutral chlorine adds one electron and it becomes a negatively charged ion, Cl negative. A delta H value is given for this process, and the delta H is negative 348.6 kilojoules per mole. Notice that it is negative, which means that this is an exothermic process. Whenever this takes place, energy is given off. It's exothermic. So a negative electron affinity represents a decrease in the energy of the gas when an electron is added. So where does that energy go? It flows from the gas to the surroundings. So if you have chlorine that's neutral as a gas, like let's say in a tank, for example, and then all of a sudden you introduce electrons to it, you will now form Cl negative as a gas, but what will happen in the process is energy will flow out. It's exothermic. How much energy flows out? 348.6 kilojoules per mole of the chlorine gas. Now, if we find that we have a positive electron affinity, this will represent an endothermic process, and energy is required to be added from the surroundings to make the electron bind to the atom. So examples of those could be the noble gases. They do not want to accept electrons very easily, so making them accept electrons requires energy to be put in. It says here that most elements have negative electron affinity values. Some of the elements that have positive electron affinities would be those that are noble gases in the far right here, or those that have full sublevels, such as beryllium and magnesium. They have a complete S shell there, so they don't want to accept another electron is the idea. We also see that electron affinities tend to get larger as we go to the right, except for those exceptions which I mentioned above. When 1 mole of bromine atoms gain 1 electron per atom, how much energy is exchanged? So if we look at bromine here, we see that its electron affinity is negative 324.5 kilojoules per mole. So that's going to be the answer here. So that's going to be the answer. 324.5 kilojoules per mole times 1 mole is going to give us an energy exchange of 324.5. Does energy flow to the bromine atoms from the environment, or does energy flow out of the bromine atoms to the surroundings? So because the value is negative, this is an exothermic reaction. Energy flows from bromine to the surroundings. Next question says, when 2 moles of lithium atoms gain 1 electron per atom, how much energy is exchanged? So we can see here for lithium's entry, it's going to be negative 59.6 kilojoules per mole. Question does say there are 2 moles involved though, so we just want to multiply by 2. That's going to be 119.2 kilojoules. The negative indicates that energy flows out of the lithium, but just the size of the energy is 119.2. And we'll say here that energy flows from lithium to the environment when lithium atoms gain an electron.